this lecture. Today we will start talking about neural nets. And what I want to do today is here. So questions? Sure. Neural net. Yes, we got the neural net on somebody's test. All right. Yeah. So what I want to do is I would like to talk about what's called vector calculus, which means you can take derivatives of stuff which has a lot of coordinates to it, not only one. It's a fancy name. That's what it means. Okay. And we will talk about what's called differentiable programming and backpropagation. And after that, a few things that you need to know when you use neural nets. That's basically the first general lecture on neural nets today. So we'll have Thursday this generative AI lecture from our industry person. Next week, one lecture I'm planning to do on convolutional neural nets, and the other one on neural nets which tries to have some memory. Recurrent neural nets or more recent versions, long-term short memory, maybe tiny bit of transformers, we'll see. I'm not fully decided on the details of that lecture yet, but basically next week we will have 2 more neural net lectures, then it's spring break. Okay, very good. So what do we do with this? Let's start with very basic stuff. You got a function, and what was the derivative? So the derivative of your function at a point A is defined by take the difference, you bump from A to A plus T, and you divide it by T, okay? Let me try to visualize it. Here I am at A. I'm bumping to, say, A plus some number. Then I'll look it up. Here it is, okay? But you could also bump back to a negative number. Here it is. And let's try to look at this definition and try to visualize it, because this is very much relevant to neural net discussion that comes later. Okay. Yeah. So here is this dot here is what? It is FA, right? This dot here is FA minus some number. I called it T2. This dot here is FA plus some number. Let me try to zoom in. Yes. Okay. Now, what was the definition doing? It was taking differences. It was taking FA plus T1 minus FA, literally looking at this difference and dividing it by the difference here. What was it? Run divided by rise. I always confuse that. Rise over whatever. So I always confuse those words. Okay, so you divide this by that. You know, I bumped it this much, how much the function changed. Or you could also bump the other way. Then it bumped from here all the way up there. There's more bump, looks like. And then you divide it. But then to arrive to a, instantaneous situation, you make that t go to 0, which happens at the limit. And if you end up actually being able to get a number off of this, that's your derivative. For not every function will make sense of this one. Sometimes you will do from left, you will do from right, you will get a different number. And that's a function you're not able to differentiate. Okay, we will work with differentiable stuff. All right. Now you could also take the second derivative, right? Probably. And I'm not going to bother writing definition of the second derivative this way. It will be very cumbersome. You first do this and do that once more, because second derivative is doing derivative of this guy. But intuitively, let's say your function was displacement. First derivative is speed, second derivative is acceleration. All right. So what does second derivative tell you? So like first derivative is like instantaneous change, right? So how much change happened in my function when I bumped my number by t much. That's like instantaneous change. Also, you can think about it like the slope. In many ways to interpret. How about second derivative? What's your intuition about it? Yes, go ahead, Jordan. Yeah, change of the change, right? Yeah, exactly. All right. One thing we know that is I'm trying to attach meaning to stuff. One thing we know is if you know your second derivative is always non-negative, your function's plot looks like this. And what does this mean? It's called convex. What's a convex thing? A convex thing is the type of the shape. If you take two dots on it, and if you do a line segment in between, the line segment always stays above, okay? So the graph here will be a convex graph if your second derivative is always non-negative. That means rate of the change is always positive, okay? You can think about this more. This is a very nice situation that you would like to have, but you don't always have, okay? So if your stuff is not working for a convex function, throw it to the garbage. If it is working for a convex function, analyze it for convex, then send inspiration for more complicated functions. You know, there is this quote, I don't know who said this. It was a famous engineer. For engineers, models are just an inspiration. Okay? So, like if you're a physicist, you got the equation. It tells you what's going to happen. If you're an engineer, the equation doesn't always tell you what's going to happen. So the point is like, for machine learning and data science and whatnot, if you're not able to do your stuff on convex, forget about it. If you're able to do it on convex, then that's going to be your inspiration. Try to do everything looking like what it was in the convex situation. All right, let's get going. And then we have this Taylor expansion. So Taylor expansion gives you one more meaning attachment to the second derivative. So it looks like this. I can take a number x, then I can expand my function around that pivot point, say a, and it's going to look like this. My function at a, x minus a times the first derivative, 1 over 2 x minus a squared times the second derivative. Then there will be some error term. That error term could be bounded by x minus a cubed. So if x minus a is a small number, this gives you a pretty decent approximation to what your function is going to do. Okay, so that's why we would usually approximate the functions using derivative and sometimes the second derivative. And that's usually about it, because you want to be as computationally quick as possible. Okay, we will talk about after spring break a lot of optimization algorithms. And today you will already see later in the lecture why we need to talk about optimization algorithms. Almost everything is optimization in machine learning. In all those optimization algorithms, they would either use the first derivative only, then it will be called the first order method, the algorithm. And if they're using first and second, it will be called the second order method. We usually don't want to do second order because it's expensive, but if we have to, we do it. But you will never hear a third order method, okay? Usually you only go by the first and the second derivative, that's it. But of course, you're losing some information. You're taking a very complicated function, you're approximating it with just this number times the linear thing, times this number times a quadratic thing. You're treating it as if it was quadratic already, but it's probably a much more complicated function, okay? All right, then we got the chain rule. This is the core of differentiable programming, I dare to say, okay? So what chain rule? I got like two functions, f and g. You combine them, they become a new function. Then you want to look at the change in this new function, the derivative of this new guy. And it turns out that change could be looked at as change in the first thing you put in, derivative of g, times put ga inside as a number, look at the change of f exactly there. It's like, yeah, I'm not going to do too much analogy here. That's about it. Everybody seems very confident with chain rules from the faces. Yeah. F is the function itself. You got in GA. That's how you should think about it. So it's like literally chain. You go from A to somewhere, and from there you go somewhere else. It's chain of functions. Okay. And now the question is like, I build this chain. I tweak A little bit at the very beginning. What is the change at the very end of the chain? And it looks like it's given to you by combination of changes, but you have to be doing it carefully. Okay, that's the chain rule. All right, very good. And now let's try to build up our derivatives. We need to have, this was only one variable. This does nothing good for us. We need a lot of variables. Don't worry, we don't need like 5 billion parameters today. Okay. So if you got a function that goes from one variable to many, how would you take derivative of it? Well, if it is going one to many, it looks like this. This is my function, but the coordinates themselves are functions, right? The coordinates are like 1 to 1. I stack them up. I got something 1 to many. Then the derivative should be straightforward. Derivative of this guy is like literally take derivative of all this stuff, put them in the coordinates. That looks fine. And now let me try to look at the chain rule. Let's say I got some function from 1 to 1, and I put this inside my f. Okay. Now I'm going from R. What is this G doing? H is going from one variable to one variable. Then F is going from one to many. So G is going from one to many at the end. And what would be the meaning of derivative? If you apply the chain rule, you end up getting derivative of the one variable guy times F derivative on HT. That means you will get this derivative thingy. And instead of T here, you will plug in HT. It's fairly straightforward. So looks like we are okay to get a one to many function. We can take derivative of it. So far, so good. Yes. Yes. So here, for the moment, the input is only one. And that correlation will be captured when you look at the derivatives. So for example, in here, you might see, say, t to the 5. Here, you might see t to the 4. That captures the correlation between the coordinates. Okay? Yeah. So I'm not claiming this f stuff here are independent from each other. I'm just trying to see what the meaning of derivative would even be. Because it's hard to develop intuition for many variables. One variable is fairly straightforward. You look at the change, you see the slope, Okay. So far from one to many looks fine. But we will need eventually, of course, many to many. Let's go there slow, okay? All right, so many to one, how about that one? So I was going from one to many, that looked fine. How about the other way around? If my function takes in a lot of stuff and just spits in one, which could be the case, say, if you're doing classification. You put in an image, whole bunch of pixels, right? And your function may be 0 or 1, malignant or benign, or like 5 options, cat or dog or zebra or kangaroo, whatnot. That's fine. Okay, what would be the meaning of derivative here? Like, derivative should be about change. Well, I only know it for one variable for the moment. Let me try to use my one variable intuition to talk about this, which I don't know how to do for the moment. Okay, so what would be the one variable version of this? Let's say this is your point A in R2. Let's say your function is going from R2 to R, okay? And let's say you picked a direction. You're telling me, I want to change in this direction, either this way or that way. But this is my direction. That's how I'm perturbing stuff. Then I could now talk about derivatives. This would be called directional derivative. Directional derivative in this direction vector V. What you're going to do, take your point A, take a number t, this is literally one number, still I am with one variable now, multiply that number with your vector, minus fa divided by t. This makes sense, right? So this is a number because function is going from many to one. Number minus a number divided by number, you'll get a number out of it. This is directional derivative. If you have many variables coming in, and if you decide on the direction, you're going to pump things up or perturb them, then you can make sense of derivative, just like the univariate one. Okay? So far, so good? So very good question. Now, how am I going to handle all the possible directions? Okay, that's what I was getting at. So very good. So let's say if somebody gives me another direction like this way, what do I do? Okay, I can write down the same definition. That's true. It will make still sense. Let's go, So my purpose today is kind of build things up so that you see how it starts from scratch and you can end up with your neural nets. All right. All right. So since that's my motivation, you need to bear with me like 30 seconds or a minute. So let's say I added 2 vectors and I looked at the directional derivative in the addition, just like that. So there was one direction, there was another. Let me add them and let's see what the heck, I'm going to get out of it. I plug in the definition. This is t times addition minus blah. Then, then I'm going to add an artificial term, a minus t1 and a plus t1 minus fi. Now, this part starts looking like the directional derivative in this direction. This part starts looking a little more complicated, but if you think about it enough, not too long, then you end up realizing, the directional derivative in the summation of directions comes out very nice. It's summation of those directional derivatives. It's kind of surprising, but this works out. So basically, if you pick two directions, and if you're looking at their sum, and then if you're looking at directional derivative in that direction, you can just do it one by one and sum it up, turns out. Okay. So let me just picture it for you. So if this was my direction, this was, say, V1, and I got a V2 here. And then I sum them up. Suppose I got this V1 plus V2. Okay. So it turns out taking directional derivative in this sum can be reasoned by take one by one and sum it up. Okay. And that's what we are going to do to handle many derivatives. Just look at every coordinate, then sum it up. Let me make it more formal. The only reason I'm able to do this is because of this property. Turns out directional derivative behaves super nice. Okay. All right. And then what am I going to do now? Well, if somebody gives me a V with many coordinates, okay, let me write it up. Let me go a little slower here. Let's say my V is like V1, V2, Vn, right? And let's say my basis is my standard basis, like 1, 0, 0, right? You know, the basis that you have seen first time you have seen a basis. And then what am I going to do is like, I can take this V, I can split it up in terms of these bases. Since the derivative goes very nicely, I'll split up its derivative in terms of every single basis element. What am I going to do? V1, this guy. And what do I mean by V1 is this. So this is like, okay, let me be slow and tell you what am I doing here. I'm taking this V and I'm writing it up as follows. V1, whole bunch of zeros, plus 0, V2, whole bunch of zeros. All right. And all the way up, 0, 0, 0, yeah. So far, so good. This looks rather silly. Why would you do that? We are going to get something out of it. Okay. Now the directional derivative splits up. I'll see that direction as summation of these directions. And those directions are super easy, you know. They're like a coordinate direction times a number. So at the end, you're going to get this derivative is this number V1 times the directional derivative in first coordinate direction, V2 directional derivative in second coordinate direction, blah, blah, blah. And we give a special name for those directional derivatives. They write it this way. They'll call it partial derivative. The partial derivative is nothing but take a coordinate direction, do a one-dimensional derivative as you're used to there, and that's a partial derivative. Okay, that's what it is. So then this allows us to do every single directional derivative based off of only this coordinate stuff. Okay, that's how it goes. And then you collect all that coordinate stuff together, you give it yet another name. You know, these people are just like poets in love. You know, if you have a poem, it calls the same thing like 10 different names because the person is in love. So this is the exact same thing called in like 100 different names. Okay, this is just like pick a coordinate, go in that direction, see how much bump is happening. Just what's going on. Okay, so they will collect all these directional derivatives in coordinate directions and stack them up together. That will be called gradient vector. That's what gradient of a function means. This means how much change is happening if I'm going in the first coordinate direction. How much change is happening if I'm going in the second coordinate direction, yada, yada. And as a result of this, you can write every single directional derivative just by take this vector, dot product it with your direction. It will tell you how much change is happening in that particular direction, okay? Because that product, what it is going to give you, this times V1, this times V2, you're literally going to get this equation. That's what a gradient vector is. It summarizes all directional derivatives for you, okay? So we're so good. And that gradient vector is what we are going to need a lot today in our neural net stuff and all differentiable programming. Any questions so far? So we are building from standard derivative definition we knew since, I don't know, maybe high school, maybe first year in college. Okay, yes, question? Yeah. Exactly. Very good question. So and you can see it right from here. Take V and say 5 times V. It'll be the same dot product times 5. Because you're going in that direction 5 times more. Yeah, very good. Any other questions so far? And now something that is potentially a little more complicated, like, okay, I got the directional derivative. What if, like the second derivative question in univariate case, like change of rate of the rate, something like that. What if I do it here? I first pick a directional derivative, then I take yet another directional derivative of this thing. What do I get? And I'm not gonna give you so much pain about this. So you're gonna get a matrix that's called Hessian matrix. It's gonna be literally take your function, take all possible second order derivatives. Here I'm taking my function, taking 2 derivatives in the first coordinate direction. Here I'm taking my function first in the first coordinate, then in the second coordinate. Think about all your choices. You're gonna pick a coordinate first, then a second. So you have n coordinates. That means n times n matrix. That's what a Hessian matrix is. Okay. You take your function, you pull in all the second order derivatives. Now you get an n by n matrix. And this thing, the second derivative first in direction v, then u, will come out, take that matrix, multiply it from u from left, v from right. That's what it is. Okay. So this Hessian matrix is just like the gradient. It records everything of second order for you. Okay. And now, so far, does the definitions make sense? We got the directional derivative. We recorded it by gradient. Now, if I talk about like the univariate case, what's the change of rate in the rate, something like that, I'll get this type of question. Directional derivative of directional derivative. And that is recorded if you do the algebra, just like the gradient stuff. That is recorded by a matrix, and it is this matrix right here. Okay? Very good. Sometimes you would need this matrix. And then this matrix tells you something about your function. This is an n by n matrix. It is symmetric. It is real. So the eigenvalues are going to be real, if you remember from our linear algebra discussion. And we called some of them a specific name. If all your eigenvalues are 0 and up, non-negative, your function, your matrix, will be called positive semi-definite. This is the analog of second derivative being positive. Okay. So in the univariate case, I got the derivative, I got the second derivative. And if the second derivative was positive, I got this convex shape. Okay. The precise multivariate analog is this. You take that Hessian matrix, you look at the eigenvalues. If all you see is 0 and positive numbers, you call that a positive matrix. And that's the multivariate analog. Then your multivariate function will be convex. And here's a picture of a convex thing for you in the multivariate. Again, you take 2 dots, you draw the line segment in between, it still stays above. The intuition in convexity is the same, okay? And it's recorded by this Hessian matrix. So far, so good? Yeah. Very good question. We can discuss it offline, yes. So there is, people still time to time come up with a faster method for this. So that's one idea, but not a very practical one. Yes. So that's maybe what you'll see in a textbook. So I don't know why people decided to put the most computationally useless stuff in linear algebra textbooks. They teach you something called Kramer's rule for taking inverse of a matrix. Come on. It's like the worst thing you could do, right? So again, what they tell for this positive semi-definite, again, not a good idea at all. But yeah, we can discuss offline. Thank you. There was a paper even like 2-3 years ago, getting some probabilistic ideas and making it faster. Whatever. Okay. So far, so good. And now I will go back to now we did what did we do so far? We did first one variable to one variable. That's what we started off with. That's what we are used to. Then after that, I went to one to many. Then I went to many to one. Now, of course, we need to finish the discussion with many to many, right? So this stuff was all like my function takes in a lot of variables. Here it's taking 2, spitting out 1. And this is, Hessian, convexity, whatnot. It's like many variables, output only one variable, okay? Now, we need to complete the discussion by functions that takes many variables and also spits out many variables. Any questions so far? Everybody doing all right? Yeah. You can give me thumbs down, thumbs up. Not sure, you know. Okay, good. Very good. Or as I learned from my kids, mid. That means what do you think about this restaurant? Mid. That gives no information, right? So, okay. So now many to many, I got n variables coming in, k variables getting out. Now, how am I going to talk about derivatives and stuff? Well, when I say gradient of this type of function, that would mean go to these functions here. Now, what are those coordinates? The first coordinate takes in all n, puts out 1. And we learned how to deal with many to 1. We will apply it to every single coordinate. That's what we're going to do. So first coordinate, take it, create the gradient vector of that thing, put it in your first row. Okay. Do it for the second one, do it for the third one. And eventually you're going to get k times n matrix. Okay. That's what they mean when they write gradient of a function which spits out many variables. This is something you would see in literature. And sometimes this is called Jacobian matrix. Another name you would see for this thing is called Jacobian matrix. They might do just the JXF. That means this thing on the left. Okay. Now you could also ask the second derivative for this. I'm not going to do, but probably you can tell it's going to be a tensor because now matrices are not enough anymore. Because every single thing will give you a Hessian matrix itself. You're going to need to put Hessian, 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 Hessian. So it's going to be a tensor. I showed you a Rubik's Cube when we were starting the class. If you remember, you're going to get a cube. This, I will not write anything, but this you might end up using if you're doing PyTorch. Okay? Yes, go ahead. Yeah, exactly. Gradient is like if you have a function that gets in a lot of variables, spits out only one variable. That's a gradient. If you have a function that gets in a lot of variables, also gets out a lot of variables, then you will get a matrix. Okay. Other than that, they're essentially the same thing, but just essentially. Okay. So far, so good. Okay. Yeah. So that's how you set up the language, and now you can do chain rule with however many variables you would like. How this is going to go, suppose my function is going from n to k, and I go find another function going from k to somewhere else, and I put them on top of each other. Now I got yet another function, which is going from here all the way up to here right away, right? And now how would I do chain rule? It goes exactly as in univariate case, the Jacobian matrix of this H guy on the left, Jacobian of this G, plug in your F, Jacobian of this F. Now you're going to multiply matrices to matrices instead of numbers to numbers. The rest, the idea is the same. Chain rule is the same chain rule. You just need to create the correct language for it. Okay? And well, why would I care about this at all? Well, think about these variables as the weights of your neural net. We'll get there hopefully soon. So far, so good. That's the language. That's, to make sense of stuff, I have to tell you all this. Yeah. I was going to say sorry, but I'm not even sorry. Yeah, I will tell you all this. That's good stuff. Okay, right, let's go. Now, that's the first part of today's construction. Now we know how to talk about derivatives with many variables. Great. Now, in practice, what kind of functions I could use for optimization? For what kind of functions I could compute the function and also its gradient or Jacobian and whatnot, okay? So one class of functions that we are able to do this somewhat efficiently is the type of functions that are represented by what we would call a computation graph, which is almost always a directed acyclic graph. Let me tell you what that means. A directed graph is a graph where you have edges with directions. They're pointing to somewhere, okay? That's the directed part. Acyclic means there will be no cycle. Here, there's a cycle. So this guy is not a directed acyclic graph. and graph is graph. Okay, that's about it. Okay. For example, this one is a directed acyclic graph. As far as I can tell, there is no cycle. If you see, tell me. I made it up when I was writing the notes. Right. So this is fine, for example. It doesn't look so fine, actually, when you look at it. Okay. So now the point of this directed acyclic graphs, in short, DAG or DAG, is like they can be ordered. What kind of ordering I'm talking about? I'm talking about something that would resemble like cause and effect, but not really. Okay. So this graph, you can order it in the following way, where every node is affected by stuff before it, not after it. That's why it's like mimicking cause and effect. Now, hopefully something you're going to do next year is not affecting what you're having now. Hopefully, if the universe is as we experience or think we experience it, okay? Right, so that's what it's trying to do. So far, so good. That's a DAG. And we have seen this in causal inference lecture. You're going to see it in neural nets. This is all over the place. If you study dynamic programming, you'll see this again. Somehow, this is what we are able to do as humanity. It turns out, we draw this directed acyclic graphs and try to use them for computational purposes. Okay, and this ordering is called topological sort. So don't ask me why. So if you give somebody a directed acyclic graph, you can call a topological sorting algorithm. It's going to turn it into this nice form. Okay. And people still think about better topological sorting algorithms. I don't keep track of what is the best one. Okay, now let's actually show you how this differentiable programming idea works out. This is a directed acyclic graph. And, let's say these are your input variables, and they go connect to other nodes. And these edges could have weights. And the nodes are going to be doing something to their input. So this node 5 gets in 1, 2, 3 variables. And it does something to them. And the outputs get shipped to 2 other places. Okay. So this node 5 is a function that each 3 variables spits out 1. And you're allowed to put whatever function you like as long as it's differentiable. Okay. Here you can think about it as spitting out 2 or spitting out the same thing twice, depending on how you describe it. But that's maybe a better way. For now, think about it as getting 3, spitting out 2. Exactly. Okay. Very good. So and then this, people would call this stuff neurons. And then when they put something out, it's called a neuron is spiking. Okay. I don't know if it's a good analogy, but that's part of the lingo. I actually took a neuroscience class last year to see if it is actually similar or not. Maybe vaguely, but not so much. Okay. Exactly. That's a very good question. So we are gonna want to spike in a smooth way because we want to take derivatives. Neurons are not like that. They're all or nothing. Exactly. So we'll get there very soon. A couple of minutes, we're there. Okay. Now let me go through this directed acyclic graph you're seeing. So you will get some input stuff. And then off of those input stuff, here I got 3 inputs. Off of those input stuff, I'm creating more variables. Think about the output of every function as a variable. Call the output of this guy x5. Okay. Now you got a whole bunch of more variables created off of your functions. And the thing at the very end is the output of your computation graph. You start from the beginning, input, whatever you see here, spit it out from this neuron is going to be the output. Okay. So X capital N in this language is the function represented by your computation graph evaluated on input variables. So far, does stuff make sense? Wow, I got a class of geniuses. So if this all made sense, pretty good. All right, very good. Now what do we do with this derivatives and stuff? I'm getting there. So one thing that we need to make clear before we do anything else is we are interested in this topological sort or this directed acyclic graph because of this. When I take a node, I see what is coming before that. That's called parents of that node. Okay, don't ask me why a node has 5 parents. All right, so that's the language. Okay, so the nodes that are coming towards that one with this directed edges, they are the parents of that node 5, for example, which is 1, 2, 3. Or like, what is the parent of node 8? 5. Only 5 looks like. Okay, so the nodes that are coming before in your order are the parents. All right, very good. Now here's our backpropagation algorithm. So before I start describing what's the idea in backpropagation, it is like I tweak my inputs a little bit. The output is going to get tweaked, but it's such a complicated function. How does the gradients work out? How is everything in between getting tweaked? How do I keep track of it? That's what's called backprop. So you propagate the change backwards. That's what's going to happen. Okay. First, you do a forward pass. What does that mean? You put in your inputs, you compute everything in your graph. That's a forward pass. From inputs all the way to outputs, also things in between, I compute them all. Okay. Things in between sometimes would be called hidden layers, because you see what you put in, you see what you get out, you don't see the stuff in between, say. But we need to compute them all. That's the forward pass. Now we go for the backward pass. How does the backward pass go? It's rather simple to describe. You initialize the last derivative being 1. If I take derivative of something with respect to itself, of course, it's going to be 1. So you initialize the last zn to be 1. And then you initialize everything else as 0 at the beginning. These are derivatives, okay? Now we are going to go compute those gradients. Then you start backpropagating. You take a zj, and you look for all of its parents, and you go for derivatives of the functions that was coming towards your zj from those parents. Okay. That's what you do. And this looks like, well, is this doing anything at all? But it actually works out. This is all you need. Okay, so I'll try to explain this a little more. But before I do, if you ask me why, it's literally you write out the chain rule, that's what comes out. Okay, so you're taking derivative of f with respect to a variable. And then from that variable, you got this ith function coming off. You first take derivative with respect to that, and this, etc. So if you just write down the math, this is what comes out. The main point is, forward pass, you compute stuff. Backward, you need to do derivatives backward because of how chain rule is set up. So let's look at the chain rule. Where is my chain rule? Yeah, right here. So my function is h. And when I take the chain rule, I got gradient of f, g. Okay. So what's going on in the backprop is like I computed this in the forward pass. I computed every numbers and everything on that node. So you plug this in to your first gradient. So you have this now. Then on top of it, you add this later. So you have to go backwards just because of how chain rule comes along. Okay. But the point is, I did a forward pass, I did a backward pass, I'm done. Usually taking derivative is much more complicated than just computing the functions. Usually you use much more compute. But here you're using almost the same amount of compute. Okay, that's the magic of this thing. So derivatives are almost immediately given to you just by how you set it up. And that's what backprop algorithm essentially does. Okay. So it just backpropagates through derivatives. That's it. Okay. So you need to stare at this a little bit. I'm going to put a whole bunch of resources today on our canvas. A lot of explaining videos, also a notebook. So you need to like stare at this a little bit. It will click eventually. Okay. So, but at first sight, it will look like, what are you talking about? At least that's how it looked to me when I just first saw this update rule. Then I had to think a little bit to understand this is actually implementing the chain rule. Okay. All right. So that is what backpropagation algorithm does. And yeah, apparently I was writing kind of magic when I was doing the notes. Okay. Now, so far, so good. Any questions? Like, we set up this vector calculus and we set up this computational graph so that I could do vector calculus on them. Maybe small digression. So people keep trying to improve these constructions. Like, do I have to create the entire computation graph? Can I do it like dynamically? Can I just compute the stuff I need on the go? A lot of ideas. You know, like big libraries, PyTorch and TensorFlow. Google started yet another one called JAX. And JAX started because of some nerds trying to improve differentiable programming. They are trying to do this stuff more cleverly and in a sort of functional programming way. Okay, so there is still a lot of people thinking on this. So today, as I said, I'm going to put a whole bunch of resources on Canvas so that you look at which one you like. Okay, not a whole bunch. I don't want to overwhelm you. Some good resources. And at the end, I put an open-ended question for you to just think about. If you are given a lot of resources and say you got pretty good software engineers in your team, and you are the brain of the team, they're going to code for you. How would you come up with a memory-efficient backprop algorithm? This still has immediate dollar implications. Okay, I'm not saying I know the good answer, but I think it's a good thing to think about. If you save everything in this computational graph, it's not so cheap. Right? So I did not talk about memory aspects at all. I just told you the math, and it works out fine. But that's usually now not when the story ends, that's when the story begins, right? So you figure out the ideas and you have to actually go execute it. How would you come up with a better way, which is more memory efficient? Just an open-ended question. You guys probably have better ideas than I do. All right, so that's so far computational graphs and backprop. Now let's actually go start looking at some neural nets. So this story is actually old. So first look at here, then I'll walk you through the story. So the guy who was sometimes called like a pioneer of machine learning is Marvin Minsky. I think he was in MIT. And actually, it's very funny that this guy is called father of machine learning because he was kind of against machine learning at the same time. So I'll tell you the story. So back in the day, they had this perceptron algorithm. What is perceptron? It's literally written here. You take a linear thing on top of your x. This is your linear multiplied with your variable. Then you add a bias. And if it is bigger than 0, you spit out 1. If it is less than 0, you spit out 0. So spitting out a bit, okay? And that's all sometimes called this H after Heaviside, the guy who first talked about this, I suppose. Let me try to zoom in. Okay. And then you try to come up with the best weights and biases so that suppose that kind of function does good binary classification for you. And then there is technical reports / news items by, I think, Navy Research Office in the 60s. They were claiming perceptron is going to think and feel and talk, a whole bunch of stuff. And then this Marvin Minsky, being a serious scientist, he wrote a book called Perceptrons, where he's literally talking about what perceptrons cannot do for you. They suck. That's the point of the book. Okay, so that's very funny. And one example he came up with was he was saying perceptrons cannot even implement this truth table for XOR. Right. He's pushing it to the limit to make a point. So, I'll show you how you can do this with just 2 layers of perceptron instead of 1. Then we will start talking about neural nets. Okay, so this is our good XOR. What does it do? It just checks if the 2 bits are the same or not. If they are the same, it gives you 0. If they're not, it gives you 1. If any of you is prepping for job interviews, a lot of lead code problems are solved by XOR. So you better learn it if you're going to go for interviews. Okay. And then Marvin Minsky was saying, look at your XOR. It looks like this if I plot it. 0, 0, 1, 1, 0, 1, 1, 0. And this perceptron thingy is a linear thing. Can you come up with a linear cut that separates this 2 from that 2? No. So you cannot even implement XOR with a perceptron, so it is useless. That was one thing in that book. For fun, if you want, you can go look up the book. It's probably somewhere online. And now you can stack perceptrons on top of each other, and you can start implementing more complicated functions, starting from this XOR. Of course, this is kind of a cooked up thing. Let me show you what it is. So we are going to implement XOR by this way. We want take your 2 bits, put an AND gate on them, then put a NOT, then take your 2 bits, put an OR gate on them. Then if you do AND, apparently this is equivalent to XOR truth table. You need to work it out, but that's what it is. They want to implement this with a neural net. okay? And since we know bits are 0 and 1, and we are allowed to mess up with the weights all we want, we are going to cook it up so that this neural net will implement this, okay? So literally this H1 here will be this AND. And by pushing a -1 and a -half, you're doing the NOT. You have to think about it to see that's what's going on. And then this guy will be this OR. And we're going to combine them as AND, and then this thing literally implements XOR. And this is a plot of that thing, okay? And this thing is called multi-layer perceptron, MLP. And that's kind of the building block for many things still to this day. Okay, we are not going to use this type of activation functions. Where was my activation function? This Heaviside type stuff. Yeah, it's actually right here. Okay, so the weights in that graph, if you put them into 1, 1, and then put -1.5, we are doing here. If your 2 bits were 1, 1, bless you. Apparently, you get a dot half, which is bigger than 0, and your function turns anything bigger than 0 to 1, so it's going to spit out the correct bit, okay? But the problem with this function is, as Owen was very nicely saying, it's not like continuous or differentiable. It's just like actually like a neuron. It's a 0, 1 thing. And now I cannot use my derivatives and stuff on this. And then it kind of, like, you know, I had all this monster machinery, now it just doesn't work for this. So, but the workaround is pretty easy. Start using differentiable activation functions, okay? So I'll show you a whole bunch quickly, then I'll move over, show you less that I keep in my mind. I don't keep all these activation functions on top of my head, but these are the common ones. And I call them neurons that behave, meaning that these are activation functions that are differentiable. If they're going to spike, you feel they're going to spike. Okay? That's how it is. So these are common activation functions you will see replacing that Heaviside 0, 1 bit. So sigmoid, probably you have seen this, 10H. Soft plus, we have seen this before in this class. And I'll talk about RLU and this leaky RLU soon. And I don't think I will use the swish, but apparently it's used. Okay. That's like a whole bunch of activation functions that you can put on your neurons if you like to. And here is these 3 you would see all the time, sigmoid, 10H, and RLU. And the only thing I want to kind of emphasize is the sigmoid function, 1 over 1 plus e to the a. The plot is like this. We have seen this in logistic regression before. But in logistic regression, we were not thinking about derivatives. We were only thinking about the values, and we were using it for classification. It was fine. Now, if I'm going to use it for an activation function, I'm going to start taking derivative of it, right? I'm going to start creating gradients off of it. Now, if you take derivative around here and there is no change at all, almost. So the derivative is going to come out as 0. So if you put in a lot of sigmoids in your activation functions, part of your directed acyclic graph may not be propagating any gradient at all, just because of this function gradient behaving kind of nasty. So this is something you need to be aware of, okay? We'll get to that soon. So when you create your neural net and start training it, first things you need to think about is either exploiting gradients or vanishing gradients, which means some of your gradients might become too large, more than you want. It starts dominating everything else in your huge neural net. You don't want that. Or it may stuck somewhere. There is no change there at all. So those neurons are like that. You don't want that either. Okay. So 2 things you always need to be careful: vanishing or exploiting gradients. Okay. And this, I hope, kind of shows you how that can happen. This is not the only case that can happen, of course. Okay. Now, how would you train a neural net? Suppose, we created our computational graph. We are allowed to mess with the weights. And that's our training, essentially. So when you create the architecture of your neural net, the neurons are fixed. The activation functions are fixed. What can you change? The weights between those neurons. As soon as you decided on the architecture, the discrete part, the core is fixed. You can mess with the weights. That's all good. Okay? And that's what's going to happen through training. The architecture, well, there were some people who were talking about evolving topologies of neural nets, but some of that never took off. I don't know. Some people were also thinking, as I train, let me keep also change the structure of the entire neural net, better for my application. That sounded like a good idea to me, but some of it never took off. I did not follow up. So there were some people thinking about this, like evolving architectures along the way. Right. Okay. Now let's do the stuff we know how to do. So I got the weights of my neural net. And imagine that's like a function where this theta parameterizes the weights, and your data is this x. And suppose we are in the supervised learning situation where data has labels, okay? Then how am I going to train my neural net? I'm going to go pick my loss function. And on my data x with parameters theta, my neural net will spit out a yes. And I'm going to check it against my label. Then I'm going to put a loss function on it. And you're going to do this through all your data, sum it up, or average it over. And you would like to find the weights that minimizes this loss. Okay. For example, when I said DeepSeek is an open weight neural net, I mean they literally publish this weights. When you know the weights and you know the architecture, you know the neural net. Okay. That's how you train a neural net. You design a neural architecture, you put your activation functions as you like, then you start training it through data. Right. So let me see if I can show you something fun. Let's see. Give me a sec. TensorFlow playground. Yeah. Here it is. Yes. Okay. Things working out. Very good. So here you see a neural net. We decide on our data set. Okay, let's say this is your data set. And you decide on number of layers you're going to put. Of course, I put a link to this on Canvas as well. Then you decide on your activation functions. I don't know, let's say RLU. We did not talk about regularization yet. We will talk about it after spring break when we do optimization. This is a trick to avoid overfitting. Suppose, and we talked about at least L1 and L2. If you remember, in the very first lecture, I talked about norms. So this is the norm you're picking for avoiding overfitting. And then you also pick like a regularization rate, which means the number you're multiplying that norm with. You'll learn all this, don't worry. And then you pick a problem type, all right, and you start training. Okay, so let me put in some more stuff in. Yeah, and since I just put it randomly, this stuff may not work at all. Let's see. No. So I created a neural net which doesn't work. So you can play with this. Let me see. Maybe go to 10H. Yeah, this time it worked, you see. Literally, you see the output of the neural net on the right. And epoch means how many times you're going through your data. One epoch means going through it once. Here it has already done 176 epochs on the training data. Okay? That's how a neural net looks like. If you're too tired, instead of watching Netflix, you can play with neural nets. Okay, just kidding. So anyway, let me get back to our lecture. But at least I wanted to show you the thing as a concrete thing before I keep talking more abstract. Okay, that's like how you train a neural net. You start. So how do you start the training? You need to initialize those weights somewhere, right? You put some random numbers to those weights and you start training. The weights get better and better. It starts being a better approximation to the problem you're trying to solve. However, where you start them actually has an effect on where you end up. Okay. If the training loss would be a convex function, there's only a unique minimizer. Where you start doesn't have any effect at all. Okay. But if your stuff is not convex, for example, imagine your function looks like this, the plot. And then if you start here, initialization, you're likely going to end up here. Likely your neural net is going to get stuck. But actually, you would like to end up here. This is the local min. Okay? And if your function is super nice, like it is convex and whatnot, so okay, sorry for this, but it was just an illustration. So let me put back that illustration. But if your function will be convex, you're always going to end up at the min. So for convex, where you start would not change anything. But very rarely you will have a convex loss function in your application. So where you start changes something. Some people worked on it though. There is something called convnet. If you want to look it up after the lecture, you can look it up. So convnet, I think. This is a group at CMUSD called Kelter's group. Kelter's. CONV. It's short for convex. So they try to create some architectures which is looking like convex, so you will avoid these issues. Of course, when you push it to look like convex, it becomes a lot less expressive. You cannot do everything with that. But if their stuff fits to the problem you're trying to solve, you're in luck. Likely you'll avoid a lot of issues. That's what I was trying to say. Okay, first you initialize, then you start training. And how are you going to train? You're going to run some optimization algorithm in the weight space. So all the weights of your neural net, suppose you got 1 billion of them. Now you're talking about 1 billion dimensional vector. And you're going to find the best vector you can, okay? And now you started somewhere in that world, you're going to travel around and you're going to try to find the best one. How do you do this? You run an optimization algorithm, which we will talk more extensively after spring break, okay? But a typical one would go like this. Take a gradient of your loss function at your current weight configuration, put a learning rate next to it, and take it minus from your current configuration. You're updating your weights this way. This is a typical one you would see all the time. You'll keep doing this iteration. Now I update it to this, I do it again. I go take my gradient again, one more update, one more update. As long as I'm improving my loss, I'm decreasing it, I'll keep doing it, okay? Very good. And of course, warning, this is just like a prototypical optimization algorithm. This is literally gradient descent. This is not the algorithm. There's several options. And I'll try to teach you the most common ones so that you're aware which one you're picking when you run some library, okay? Right, very good. Of course, also you need to think about how you change this learning rate. We will talk about this also. Now, looks like we're all good. We can just take this neural net, start training them, feed them with data until they grow, and then they'll do the things for us. What are the things you need to watch out for? First thing is this exploiting or vanishing gradients problem. Let me try to illustrate it. Suppose you're like taking derivative of your loss function with respect to some variable L. And if L plus 1 is ahead of it, you're taking first derivative with respect to that, then taking that L plus 1 with respect to L. How that's going to look like? Suppose your L plus 1 was a function of L. Let's say this was one layer, L, and G is the weights going from layer L to layer L plus 1. You can think about it that way, okay? And then what does this derivative mean here? It means literally gradient of that function. How about that one right there? If that L was like a function, kind of complicated, that's going to be like the Jacobian of that function. So at the end, this expression here is essentially Jacobian times gradient, okay? And I only took derivative with respect to one variable. And imagine you're back propagating. Like this is only one, then you'll take one more derivative, one more, you know? So it's going to keep like multiplied on top of each other. So you will have like a whole bunch of Jacobians or gradients like multiplied with each other when you're taking derivative with respect to a variable that was early on in your architecture. So if any of those gradients like died, it might kill all your backprop for that variable. That's one thing you need to be aware. Or if they like exploded so much, it might become too sensitive. So fixing the exploiting issue is easier. This is the typical trick called clipping. If my gradient was G, and if I'm afraid it might be getting too big, you multiply that G with minimum of 1 times a constant you like, this like say half, whatever constant you put, divided by norm of that G. So this, let's say if this norm of G is super big, this is gonna come out of it, C times G divided by norm. So G divided by its norm is gonna make sure the norm is now 1. And you're multiplying it with half. So the norm of this new update is gonna be like half. So clipping kind of takes care of a lot of exploiting issues. Vanishing seems to be more tricky. Clipping is probably not the only trick, but it is good enough. So very good. It does the job most of the time. Now, for saturating though, you need to be more careful. So let me walk through a very common activation function, this rectified linear unit, RELU. What is it? It is literally this guy. You put in A, it spits out maximum of A or 0, which means if A is less than 0, you're going to get a 0. If it is bigger than 0, you're going to get back your A. Also, it's like A times that heaviside 0-1 bit function that we were kind of trying to avoid. And people would usually do, let's say, something linear on your variables X, and then put it inside this activation function. That's what you get out of that neuron, say. What happens if I take the derivative? You get out your thing back, which is nice, but then times you're either going to get a 0 or 1, depending on if this was positive or negative. And depending on this weight configuration, this could easily be negative. And this will just die. Okay, you don't want that to happen. Okay, yes, go ahead. This is like training not going well. You're keeping epoch after epoch with data, not much is changing, not because your data was bad, it was because the activation functions you created in your neural net wasn't done carefully. Clipping will help with exploding, like getting too big. Vanishing, which means this derivative dying, being 0, nothing is changing at all. Derivative is like the change, right? So if it is not changing at all because of the way you created the activation function, that's a problem. If it is not changing at all because you arrived to like an optimal place, there's nowhere better to go, then that's a good thing. Okay? So you need to be careful on the activation functions you put, not to have the vanishing gradient problem. And I'm just going through one. I just started. So I'm talking about this RELU. As it is, even though it is commonly used, it can easily give you this vanishing gradient problem. And vanishing gradient problem is given by saturating activation function. So think about the sigmoid graph. It was saturating, but in two ends. There was no change. That's the issue. Now, how do you fix this? So people come up with a lot of ideas. So one of them is called like leaky, RELU. All right, so what is leaky? You put a new parameter alpha between 0 and 1. Instead of taking max of 0 and A, you take alpha, A, and 0. It makes it a little better, but still not smooth and nice. It still has a max in it, which is not smooth. And of course, writing notes is not the most exhilarating activity. So I was thinking about some smooth jazz and whatnot. So you can make it smooth with this little trick. So that's called ELU. What do? You put your alpha, and you put e to the a minus 1 here, and only a here. The point is, the switch happens when a hits 0, and there the switch is rather smooth. So this thing is much better than the standard RELU, because the gradient does not die just because of what it is. Gradient can die if you don't want any change. That's a good thing. But gradient shouldn't die because of your activation function being kind of messed up. Okay? All right. So, and there is one idea called residual nets, which we will talk briefly when we talk about convolutional neural nets next week. That also kind of avoids the vanishing gradient problem, because this residual stuff does something and always adds a copy of the data next to it. And this always gives you at least a 1, so it does not go to 0. We'll talk about this later. And the So far, so good. This is vanishing and exploiting gradients issue. I have a minute or two left, and I'm almost done, so that's a good thing. That's the first thing to watch out for. The second thing to watch out for is initialization. Where you start those weights matters. You can end up in very nonsense places if you don't initialize well. There are a whole bunch of heuristics. One of them is named after Jan LeCun, LeCun initialization, HE initialization, and this GX sometimes is only called with G, sometimes with X. It was two people, I think Gabor and Xavier, their heuristic. These are all like some probabilistic stuff to make sure you're not starting from a very pathological place at least. At least you're starting from like a typical situation, so you hope you're not gonna get stuck too bad, okay? And then there is also some data-driven heuristics. This is like one recipe probabilistic for whatever you're doing. And then people said, okay, let's combine that probabilistic techniques with seeing the data I have. And there's some data-driven heuristics as well. Our textbook has some links for this. If you want to look up, you can follow from there. I'll give the pointers. And overfitting. We will talk about tricks to avoid this after spring break. The buzzword is called regularization. And the last thing is like this pesky learning rates. So there's like learning rates in your iteration. And that also gets sometimes very annoying. We will talk about that later too. I'll give the pointer. We are talking about beginning of deep neural nets in the book.